Yes, good evening, student. Am I audible? Hello. Are you able to see the screen? Okay, we should start now. Okay, so first of all, we'll discuss about the assignment question of last week. Okay, then we will discuss about important concept of week third lecture. Okay, so let me share first assignment number two questions and check whether you did right or not. So first question is okay. The first question is the just a minute. First question is the functionality of citric acid in the polyamide reaction with ethylene diamine is okay. Just a minute. Hello, 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 hello. Okay, so first question is the functionality of citric acid in polyamidation with ethylene diamine. Okay, so first of all, we need to find out the structure of citric acid. Okay, so it is written here. This is the structure of citric acid. Okay, so it has a three functional group: first, second, and third. Okay, so this molecule has three functionality. Functionality means it can make bond from three sides. This is the first side, second side, and third side. So it can make bond with three sides. That's why its functionality is three. Okay, you can also draw this molecule like that. Okay, so it can make bond in all these three directions. Okay, so this type, you can say, branch type of polymer will be formed by the polymerization of citric acid. Okay, then question number two, consider the following monomer. Okay, this is the monomer. What is the functionality of the monomer? Okay, what is the functionality of monomer? So conditions are given here. First, in a reaction that produce amide link. Okay, if reaction produce amide link, amide means it will react with amine. Okay, so NH2COH, so it will be NH2. Then okay, so it will be amide bond. So what question is asking is, what is functionality of F of monomer? Okay, if it reacts to amide link. Okay, amide link means NH2, you can write simply. Okay, in the reaction to produce ester link. Okay, So star link means it will be like that. Okay, and there in a free radical or ionic reaction through C double bond, CC double bond, if it is reacting to CC double bond with a free radical or ionic addition. Okay, so we need to find out the functionality of this molecule. Okay, so first of all, when it will react with amide, okay, it can react only with COH, because COH group only can react with amide. Okay, so only functionality is one. So in first group, functionality is one. In the second, in the reaction that produce ester link, okay, so ester can be made by these two O and COH also. So total three functionalities there. And in last, in a free radical or ionic addition reaction through C double bond. Okay, so here this is the double bond. You can see one double bond, second double bond, third. So they are first and second carbon atom which can make bond. Okay, so functional group are two, then three and four, and five and six. So total six groups are there. So right answer is one, three, and six. Okay, so C is right answer of this question. Okay, means this this monomer, suppose this is the monomer. If we are telling that this is the monomer, so this monomer is same. However, it can make different number of bond with different molecule. Okay, so the functionality is also not fixed quantity of any monomer. Okay, it is changed particularly how and from which molecule it is getting reacted. Okay, which type of compound it is getting reacted. Okay, it is dependent on that also. We cannot say that this type of big molecule has this, their functionality can be vary. Okay, this big molecules functionality can be vary, and it is depend on the reacting molecule also. Okay, so this is the gist of this question. Which if somebody is getting sorry. Okay, okay, fine. So now we are going to move on another question. Next question. Two question we have already solved. Just a minute, somebody. Okay. So it is written here, which I explained you just now. Okay. So COH group, COH can participate amide formation. Okay, it is very common for protein also. Okay, in protein also this type of bonds are made, which is called amide bond. Okay, so it is for COH. Then both OH and COH can participate in ester formation. Okay, so there are how many OH? Two OH group and one COH group are there, and they have finally three double bond. So there are six functionality. Okay, so for double bond there are six functionality. For ester formation there are three functional group, and for COH participant, or we can say amide formation, there is only one functionality. Question number 3. Which of the following monomers are most suited for cation polymerization? Okay, cation polymerization means if you can say, okay, this is the cationic polymerization. Okay, so when it will be attack, suppose it is attacking on C double bond C double bond C, then it will make what? You can say this is the double bond, suppose. Okay, so it will make N, then CH2. Okay, so it is making this cation. Okay, so how, if we are able to stable this cation, then it will produce uh, more polymerization. Okay, so we need to find out the stability of this molecule which form after cation addition. Okay, if after addition of cation it is making more stable compound, then we can say yes, polymerization will be there. And if it is not stable, then opposite, that polymerization will not uh, occur, or it will be occurring very slow speed. Okay, so that we can guess according to its structure. Okay, its structure after forming of cation, after addition of cation with the molecule. Okay, so here we will discuss about the structure of this compound. Okay, so monomer that are not suited for cation polymerization, sorry, monomers are most suited for cation polymerization are those that cation electron donating substance. Okay, why it is cation? Because, so I just give you one example. Suppose two bond here and one n plus is coming here. Okay, and when it is making bond like that, okay, sorry, it will not. When it is making bond, okay, if there is one electron donating group, EDG, electron donating group. Okay, if there is some electronic donating group, then it will stabilize this cation. Okay, and the polymerization will be high. Okay, the rate of polymerization will be high. Okay, so now we will discuss about this structure of various monomer, and we will finalize that whether this polymerization will be happen, or it is suitable for polymerization or not. Okay. Okay, so we already know like alkenes, alkoxy, 1,2-dialkyl, phenyl. These substitutes stabilize the propagating cation center. Okay, so if we discuss about the first molecule, methyl vinyl ether. Okay, so this is the methyl vinyl ether. Okay, so this is the compound methyl ether in ether. So if cation will be react here, okay, you can say n plus, when n will react here. Okay, no, sorry, suppose I am assuming that n plus are taking here. Okay, so what will happen, carbon, it will be plus charge will be here. Okay, so oxygen molecule has two lone pair, so it will be shared. Okay, and this molecule can be stabilized by the resonance. Okay, similarly, 4 vinyl pyridine. Okay, so 4 vinyl pyridine is this one. Okay, 4 vinyl pyridine, this is the group. Okay, because if we start numbering from here, so it is first, second, third, and fourth. Okay, so 4 vinyl pyridine. Okay, so when any positive charge react, okay, it will plus charge will be here. Okay, then this bond will shift here, and again plus charge will be there. Then this bond will be shift here, and again plus charge will be shifted here. But nitrogen has one lone pair, we know. Okay, so it can carry this positive charge. Okay, because already lone pair is there, so this lone pair can be used for the for making bond. Okay, or to stabilize this positive charge. Okay, so this molecule is also very suitable for uh, polymerization, which we are talking about, cationic polymerization. Okay. Okay, so we have already discussed about these two molecules. Okay, which are, this is suitable and it is also suitable. Okay, now we will discuss about some more molecule like vinyl chloride. Okay, so this is the vinyl chloride. Okay, we see vinyl chloride. So when n plus will be react here. Okay, so it will be positive charge here. Okay, so what will happen, but it is chlorine also electron withdrawing group. Okay, so it will not stabilize this carbon atom. Okay, it's cation. Okay, then again we can discuss about this vinyl acetate. Okay, this is the vinyl acetate. So when N plus react from this side, okay, positive charge will be here. Okay, and is oxygen is electron withdrawing group. Okay, because negative charge also will be here. Okay, this bond will be also shifted here. Okay, delta negative. So finally this electron will be pulled like that. Okay, so that's why it is also positive charge will be created at that center. Okay, that's why it will not be able to stabilize this vinyl acetate also. Okay, then which remain methyl vinyl ether. Okay, so where is methyl? This is the this is the methyl vinyl ether. Okay, here also if N plus react from here, it will make positive charge here. Okay, so it will be delta negative. Okay, so it will be delta positive. Okay, so it is also contradicting because both are delta positive. This carbon is delta positive, this carbon is also delta positive. So it will also not stabilize this carbon atom. Okay, so so the final answer will be methyl vinyl ether or 4 vinyl pyridine. These two molecules are able to circulate or stabilize this positive charge which is produced due to cationic polymerization. Okay, so this molecule will polymerize favorably by cationic polymerization. Okay, I think somebody in waiting room. Let me check. Okay, if you have any doubt, you can ask. Okay, if you have doubt in any question, you can ask here. Okay, I think it is clear. Okay, the cationic polymerization you can explain by the structure of molecule after addition of cation. If it is, if molecule is able to stabilize this cation or this positive charge due to produced due to addition of cation, then it will be polymerized well. Or if the cation produced after the addition of cation, if this positive charge is no if the molecule is not able to handle this positive charge, okay, or if it is creating if the conditions are not favorable to adjust this positive charge, then we can say this molecule will not favorable for polymerization. Okay, now question number 4. The question number 4 is question 4 is numerical type. Okay, so the weight average molecular weight. See, this is the weight average molecular weight of equimolar mixture of epidic acid and hexamethylate diamine is found. This quantity 22,600. Find out the conversion of the reaction. Okay, so we need to find out the conversion. How much conversion we could have. Okay, so it is already given here. What is given? Weight average molecular weight. Okay, so weight average molecular weight is already given here. Okay, and we need. So if weight average molecular weight is given here, okay, we can find out XW. Okay, weight fraction of polymerization. Okay, it will be around 22,600 divided by molecular weight of this group. Okay, molecular weight MO. So you can find out how many carbon are there. So carbon is first 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Just a minute. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So carbon is 12. Then nitrogen 12 into 12. The nitrogen is first, second. So 2 nitrogen. Okay. So 14 into 2. Then oxygen, so two oxygen are there. Okay, so solar into 2. Then hydrogen, so how many hydrogens are there? So 2, 4, 6, 8, 10, 12, then 14, 16, 18, 20. 20, then 21 and 22. Okay, so 22 into 1, you can say. Okay, so if you find out, you will able to get the exact value. Okay, so it will be 144, then it will be 28, then 32 and 22. So it will be how much? 8 plus 10, 10 and 16, then 1. So 8, 10, 11, then 12 and okay, so 226. But this molecule is the repeating unit contain two monomer. Okay, so it will be divided by 2. Okay, so OMA will be divided by 2, so it will be 113. Okay, so you need to divide XW about 22600 divided by 113 first. Okay, so how much you will get? You will get around 200. Okay, so you are able to find out XW. Okay, mole fraction, you can say average molecular weight. Okay, degree of polymerization, weight average degree of polymerization. Okay, so here it is given weight average degree of polymerization XW. Okay, weight average degree of polymerization is given by this formula: 1 plus conversion divided by 1 minus conversion for equimolar mixture. Okay, first of all, we have just count out MW, MO, sorry, MO, the repeating unit divided by 2, so it is 113. Okay, we have already count. Then weight average degree of polymerization XW, we can find out 200. Then we need to put this value only. Okay, so it is already there. Okay, formula is there. XW is equal to 1 plus P divided by 1 minus P. Okay, so you need to put value here. You need to find out this value. Okay, XW already we know 200. Okay, so if you put value there you. So conversion is 0.99. Okay, this is the fraction of molecule which are converted. If you find out in the percentage, okay, you need to multiply by 100. So it will be 99%. Okay, so answer will be 99%. This is the answer of this question. Okay, let me check if somebody in waiting room. Nobody in waiting room. Okay. Okay, so now we are going to move next question. Okay, so this is question number 5. It is also numerical. It is also numerical question. The feed ratio of acetic acid and ethylene glycol that should be employed to obtain a polymer of number average molecular weight approximately 86,899 calories. Okay, so number average molecular weight is given here. This is the Mn and conversion is given here. Okay, conversion percentage is given here. So what we need to find out the feed ratio of acetic acid and ethylene glycol should be employed to obtain polyester molecule. Okay, so how much the ratio will be there? Okay, so we need to find out R. Okay, we feed the feed ratio of acetic acid and glycol that should be employed to obtain polymer which has number average molecular weight 8600 and conversion is 9. Okay, so we already know the formula. Okay, we will put the value in this formula. Okay, so the when acetic acid and ethylene glycol, if you find the value of molecular weight of this repeating unit, Okay, so you can I think it is very simple, you can do yourself. Okay, so it will be 172, and because there are two molecules, two monomers are there in one repeating unit, so it will be divided by 2, so you will get 86. Okay, then you can find out degree of polymerization, because we need to produce uh, polymer which has uh, mo- number average molecular mass 8600, when it will divide by we can say MO, it will get 100. Okay, so degree of polymerization is 100. Okay, this quantity is done. Then conversion we need to find out 0.99. Okay, it is already given. It is given. Okay, and this we find out. Okay, now by help of these two quantities, we will able to find out the R. Okay, so this is the expression. We will modify this expression to find out R. Okay, we just shift this xn here. Okay, we will find out R. Finally, we will put the value. Okay, so xn value we know and conversion value we know. So finally, if you solve this equation, you will able to find out. Okay, so R will be 1. So value of R will be 1. Okay, student, you need to memorize this formula. These are very important formula for polymerization. Okay, so if you are able to, you need to do some question. Okay, then you will only able to memorize this formula, which will be help you to uh, solve this type of question. Okay, then question number 6. Question number 6 is step growth polymerization is 99% completed. Okay, what is saying? Step growth polymerization 99% completed. So conversion is 0.99. Okay, conversion is 0.99. Then compression type question. What fraction of the reaction still exists as dimer? Okay, so we need to find out xmer. Okay, so we need to find out. Okay, so we need to find out xmer. Okay, so we already know that this is the formula of nx. If you find out any xmer, okay, at any conversion, so this is the formula. So what question is asking? What fraction? Okay, you need to find out fraction. So you need to find out nx upon n. Okay, this monomer, number of this monomer molecule divided by number of total molecule. Okay, nx by n. So it will be give you fraction. Okay, it will give you a fraction. So if you shift nx here, so xn will be mole fraction of the monomer. Okay, so this is the quantity for the mole fraction. Okay, mole fraction. This formula is to find out mole fraction of this monomer. Okay, so it is not n2, it is nx. Okay, so nx upon n will be now we will put the value. Okay, so it is asking about mm, it is asking about dimer. Okay, so dimer, so x will be 2. For dimer, x will be 2. Okay, then 1 is given here, it is 0.99. Then again p, so 0.9, then x. Okay, so it is 2. So 2 minus 1, because we are going to find out dimer, na? Okay, we are going to find out dimer. Okay, so x will be 2. So when you put this value, okay, you will able to find out the final answer. Okay, it is a 0.009. Okay, so this is the mole fraction available. Okay, and is a mole fraction, and if you find out the mole, then you need to multiply by 100. Okay, so 0.99% will be there of monomer. Okay, I think it is clear. Any doubt you can ask meanwhile. Okay, then question number 7. Question number 7 is asking what fraction of reaction mixture is still monomer on a weight basis. Now see, this is the, now you need to find out on weight basis how much weight is there of this monomer. Okay, initial before that we just find out how many moles are there. Okay, moles are there, we've just find out in the previous. Okay, Here we are going to find out weight basis. Okay, so here this is the formula to find out weight fraction. Okay, here is the formula to find out weight fraction of monomer. Okay, any monomer, you can say Wx. Okay, so Wx, the formula is this: x minus 1 minus p square, p minus x minus 1. Okay, here again, but here see, it is asking about the monomer, so x will be 1. Okay, for monomer x will be 1. Then if you put this value, x is equal to 1 and all. Okay, conversion we already know 0.99. Okay, so you will able to find this weight percent. So again, weight percent, weight fraction is very low compared to uh, number weight fraction is very low compared to mole fraction. Okay, okay, so this is clear. Now question number 8. Okay, so in an externally added acid catalyzed. Okay, so this catalyzed is added from the externally. Okay, polymerization reaction of equimolar. Okay, see, it is equimolar, means Na is equal to Nb. Okay, or you can say Na is equal to Nb. Equimolar diol, equimolar diol and diacid. Okay, so it will be diol. You can say diol and diacid. These are the monomer which are going to react. Okay, the time that was needed to react 99 conversion is 98 minutes. Okay, time is given and conversion is given. Okay, calculate the time that is required to reach 99 conversion. Okay, so this conversion to 99.5, we need to find out time. Okay, so already we know that this is the ratio, this is the formula from where you can find out extend from where you can find out the time. Okay, for the particular conversion. Okay, from here you can find out time required for the particular amount of conversion. Okay, so if you adjust this equation, you will able to find out t is equal to 1 minus p, and it will shift like there. Okay, you will able to find out this formula. Now the put the value. Okay, so conversion is initially is equal to 0.98. Okay, so we put this value here. Then COK value we don't know. Okay, no need to worry. Okay, if you solve it, you will 49 COK. Okay, so it is 98 minutes. We already know because 0.98 conversion is occurring in 98 minutes. Okay, so this is the value. Now from this value you can find out COK. Okay, COK is zero point 0.5 minute inverse. Now if you put this value for 99.5 conversion, okay, then you need to put 0.995, and COK value we already know. Okay, so if you put this value, then you will get uh, final time which required to convert this reaction around 99.5%, or conversion rate 0.995. Okay, so I think this question is clear. Any doubt up to here you can ask. Okay, okay, then okay, then question number 9. The amount of benzoic acid, let me see, somebody invited on. Okay. Now we are going to discuss about the question number 9. Okay. This is the numerical type based question. Then the question is the amount of benzoic acid. Okay. The amount of benzoic acid. Okay. So it will be, you can say, chain stopper. Okay. Add to mixture 2 mole of acetic acid and 1 mole of hexamethyl diamine. Okay. So here you can say Na is not equal to Nb. Okay. To produce polymer Mn of value this one. Okay. So its number average molecular weight is 12,000 and conversion is 99.5%. Okay. Or you can say 0.995. Okay. So these are the molecule acetic acid and hexamethyl that are reacting, and they are making minus H2O, and they are making this nylon 66. Okay. So we are adding benzoic acid. Okay, we are adding benzoic acid externally. Okay, it can be act as a chain stopper. Okay, and it will stop polymerization. So the amount of benzoic acid should be added. Okay, so we are going to add this benzoic acid so that our conversion should be 99.5% and the Mn value should be 12,000. Okay, particularly for the particular application, we need to find out only this value. Okay, so number average molecular weight should be 12,000, not more than it or not lower than it. So we need to find out the concentration of benzoic acid. For that, how we will find out, I will explain. Okay, again, you can find out that polymerization is already given. Okay, sorry, number average molecular, number average degree of polymerization is given. Okay, number average degree of polymerization, let me see. Yes, 12,000. Yeah, it is molecular weight of it is, so it will call degree of polymerization. Okay, so average degree of polymerization of Mn12 will be calculated from the total weight of molecule divided by mm. Okay, so Mi103 we have already calculated. Okay, in previous question. So if you divide this 12,000 by 103, it is the weight of complete polymer, and it is the weight of, you can say, repeating unit. So if you divide this thing, then you will get 106. Okay, now Na is 2 and Nb is 1. It is already given. Okay, it is already given. So you need to find out degree of polymerization. Okay, so degree of polymerization we already know. Okay, we need to find out ratio. Okay, so again we will degree of polymerization we have calculated. So we just modify this equation. Okay, we just modify this equation and then we'll put the value here. Okay, so we will put the value here and we will finally find out the ratio, conversion ratio. Okay, now we have conversion ratio, then R is there. Okay, so from where we need to find out, actually we need to find out benzoic acid. Okay, which is used as stopper of this polymerization. Okay, so Nb dash. So if we adjust again this equation, we will find out this value. Na we know. Okay, Nb we know, and R we have find out. Okay, so if we put this value all together in this equation, we will able to find out the number average degree. Number average. Number of, you can say, number of mole of benzoic acid for this reaction to produce this type of polymerization. Okay, and for this particular conversion. Okay, I think this is also clear. Okay, then question number 10. Question number 10 is asking which of the following molecule will give hyperbranch cross-linked polyester when condensed with acetic acid. Okay, which of the following molecule will give hyperbranch cross-linked polyester? Okay, hyperbranch. Okay, so when it will be hyperbranch, okay, when it will be react from all side. Okay, it will be like that. Okay, then it will make hyperbranch. Okay, so how it will be there if it is functional group, okay, more than equal to 3. Okay, then only it will be there. Okay, so you can see we will discuss various type of monomer here and then find out that which monomers are able to produce polymer okay, which give hyperbranch or cross link. Okay, so first of all we will discuss about ethylene glycol. Okay, so this is the ethylene glycol. Okay, but it has only functional group 2, so it can make only chain polymer. Okay, it can make only straight chain. Similarly, ethylene diamine. Okay, so it is ethylene and diamine. Okay, ethylene diamine. So it can also make it has all it is also has functional group 2 functionality 2. So it can make also chain only. Okay, chain polymer. Uh, so it is not right answer. Ethylene and glycol. Okay, so glycol has 3. So it can also make some branch structure. Okay, it can glycerol can make some branch structure, but it will make straight chain. Okay, so but it will not make hyper branched. Okay, so it is not, we can say, not right answer. Then glycerol. So this is a glycerol. Okay, so this is a glycerol. Its functionality is 3. Okay, so it can make branch from 3, and same penta penta erythritol. Penta erythritol. This is also contain F is equal to 4. Okay, so when this molecule react with this molecule, it can make hyper branch. It can make hyper branched. Okay, hyper branched polymer. Okay. Okay, then this question number 11. Consider a mixture of following monomer along with their amount. Okay, so these are the same amount, 5 and 5. So you can say Na is equal to Nv. Okay, because each monomer has 5 mole. Okay, triglycerol you can say, and H succinic anhydride. Okay, so what question is asking, the average functionality is. Okay, we need to find out the average functionality. So how many functionality glycerol has? So it has 3. Okay, similarly succinic acid has 2. So we need to find out average functionality. Okay, so F average is nothing but a weight average. Okay, we generally take weight average na. So this is only weight average. Okay, functionality of particular monomer. Okay, we will add all the summation of functionality of particular monomer. Then we will divide by total number of monomer. Okay, so it will be like that. Okay, so you, if you find out, so it will be F will be sigma F into, you can say, N. Okay, and sigma N. So if you do like that, you can find out the value. Okay, so it will be like 3 into 5. Okay, then plus 2 into 5, then 5 plus 5, 10. Okay, total molecule is 10. So it will be 15 plus 10 upon 10. So it will be 25 upon 10, or you can say 2.5. Okay, so average molecule, you can say this is, if you take average 2 and 3, then also you will get the same value, because you can say you can take simple average also. Okay, you can take simple average. By simple average we are able to get the same value, because their weightage are same. Okay, means their mole are same. So uh, this factor not affecting the overall functionality. Okay, otherwise you need to follow this pattern. Okay, to find out average functionality. on the basis of weight average. Okay, we are generally used in maths weight average. So by this way you can find out. Okay, so this is a detailed solution. It is given here. Okay, for glycerol is equal, it is 3, for successful it is 2. Okay, F. So F is given here 3 and 2. Then sigma Fi upon Ni. So 5 mole into 3 and 5 mole into 2. Then 5 into 5 it will be 2.5. I can change this question. Suppose if glycerol has, if we can say glycerol has, let me say 10 mole. Okay, and succinic anhydride has, let me say 7 mole. Okay, then you cannot take simple average. Okay, here you can take simple average. Okay, here you can take sample average 3 plus 2. Okay, 3 plus 2 divided by okay, there are 3 plus 2, and then there are two molecules, so 5 upon 2, but I leave it. Okay, don't make confusion. Okay, so if it is 10 and 7 molecule, then it will be not simple average. Okay, I am just going to explain this thing also. So it will be 10 into 3 plus 7 into 2, then 10 plus 7. Okay, so here simple average will not work, so you need to do like this. Okay, then 17, so it will be 44 upon 17. Okay, so it will be around 2 point. Okay, so it will be around 2.59, but here you cannot take it by average. Okay, here you need to find out because it is weight average. Okay, clear up to here, up to this question? I think all things are clear. If you will interact, then only I will able to understand that you have any doubt or like that. Okay, then question number 12. Question number 12 is asking the extent of the reaction at which gelation occur for the above mixture is. Okay, so gelation, when gelation will be occur. Okay, so it has one formula. Okay, in the case two functional group are present in equivalent amount, the critical extent of reaction PC at the gel point. Okay, PC means where conversion at which gel uh, gelation is occur. Okay, so the conversion where gelation is occur is known as a PC. Okay, and PC is known as 2 upon F average. Okay, F average we have already find out 2.5, so it will be 2 upon 2.5. Okay, so it will be, you will get 0.5. Okay, so at the conversion of 0.8, or you can say 80% conversion. Okay, at 80% conversion, the gelation will be occur in polymerization. Okay, so by this simple formula you can find out this. Okay, okay. Now question number 13. The polymerization between equimolar amount of acetic acid and ethylene glycol proceed with equilibrium constant uh, 289. Okay, and initial monomer concentration 2. Initial, okay, starting monomer concentration is 2. The reaction is carried out in closed system without removal of byproduct. Okay, so you are not able to remove the byproduct. Okay, so what will be happen? Okay, so the expected degree of polymerization is, we need to find out. Okay, so you can find out that equilibrium constant is already given. Okay, so xn can be find out, degree of polymerization can be find out by this formula, 1 plus k half, k power half. Okay, so it will be 1 plus k already given, half is will be 18. Okay, so degree of polymerization will be 18. Okay, then question number 14, the extent of polymerization at equilibrium. Okay, there again we need to find out the conversion at equilibrium. Okay, so it will be this is the formula. If you put this value here, okay, you will be able to find out that at 94.4% conversion. Okay, at 94% conversion, the extent of polymerization will be 0.994. Okay, for this thing. Okay, so you can say at equilibrium 94.4 conversion will be occur. Okay, so these are the question assignment taught in the sorry, these are the assignment question of week 2. Okay, now we will discuss about week 3 concepts which were taught by sir in last week. Okay, so up to here, if you have any doubt, you can ask. Okay, so I'm giving you 5 minute break. Okay, then we will start again. So we will start at 7 p.m. again. Hello, 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 Okay, student. So we should start now. Am I audible to you? Can anybody revert? Am I audible to you or not? Hello, Dhana, Dhana, Prithvi, Rajan, Meghnath. Yes. Am I audible? Ha ha. Just I am asking. So, are you able to understand the question? Means, are you understand the? Are you able to understand questions which I explained? Any doubt regarding these questions? Oh, okay. Okay, good. Okay, so now we will discuss about some concepts which were taught in week third. Okay. Okay. So polymerization with radical. Okay. So it is called radical chain polymerization. Okay. Means in first step we are making radical, and these radicals are responsible for further propagation of chain. Okay. So obviously, how much radicals are there, which will be responsible for the rate of reaction? Yes, if more radicals will be there, rate of reaction will be high. Okay, but it is also creating sometime problem. If more radicals are there, then it will make a small chain. Okay, because radicals are there, so the monomer will be distributed more. Okay, so so the length of chain will be decreased, and final molecular weight of polymer will be decreased. Okay, so generally we need to find a polymer which has high molecular weight, so it can sustain for required applications. Okay, so here initiation Ri depends the type of radical initiation process. Just a minute. Yes. So in radical chain polymerization, actually the propagation or polymerization is depend on Rp. It is called as a rate of propagation, and it is equal to Kp, rate constant, then m dot, which is representing concentration of radical, then m, which representing concentration of monomer. Okay, generally it is depend on uh, rate of propagation only. Okay, rate of polymerization is depend on rate of propagation only, because rate of initiation and rate of termination are very fast, and it is not mainly we can say propagation is already, propagation speed is already only the considerable value for the polymerization. So Kp and Kt are independent of the size of the radical. Okay, Kp means Kp means propagation, and Kt for termination. Okay, so the rate of this this rate constant are independent of size of the radical. Okay, because with time the size of radical will be increased. Okay, because the number of monomer will be increased as time pass. So size of increase, but it is keep in your mind that the rate of, so not rate, the rate constant, okay, of propagation and termination will be independent of the size of the radical. Okay, so the rate expressions are given here. Okay, so propagation we have already discussed. Then finally at the termination, so termination can be done by these two methods. Okay, termination can be explained by these two methods. First is by coupling. Okay, coupling or combination. Simply, sorry. Okay, coupling means after some time, two chains are connected together and make a complete chain. Okay, obviously, if there is a big chain which after termination, if these are combined, it will make a bigger chain. Okay, and the degree of polymerization increase 2 times. You can say, okay, just it will be double. Okay, so that's why we discussed in last week also why the conversion, at the end of conversion, the rate of molecule increase drastically, or xn will be increased drastically at the end of product. Okay, if you plot the graph between xn and conversion, okay, so it will be look like, okay. So at the end of reaction, the conversion will be increased fast. Okay. So here we are, what we are, okay. Then disproportion. Please keep your mic muted. Uh, just wait. Meganathan, can you please keep your mic muted? Meganathan, Meganathan, are you able to hear me? Okay, so we are here. Okay, so combination and yes, this is the disproportion reaction. Okay, so it here in this you can say action will be increased very high, but here action will be remain same. Okay, why? Because it is only interchanging the electrons or some atoms, small atoms like hydrogen and like that. Okay, and the polymer chain length will be, remain same after termination also. Okay, so action will be remain same, but here action will be just doubled. We can say generally just double, or double, or you can say equal or more than double. Okay, here in the combination cases. So finally we can say that uh, that termination can be done by combination, okay, or disproportion. If KTC, if KTC is equal to KTD, then you can write this equation, but it is not true always. Okay, because sometime KTC will be higher, sometime will be KT. Okay, so then this is the expression we need to find out. Okay, A KTC minus 1 minus. Okay, so you can say the fraction of molecules which are terminated by coupling, 1 minus, okay, remaining fraction of molecule which are terminated by disproportion. So the finally KT will be uh, finally the KT will be expressed by this equation. This is the corrected equation. Okay, you can say real life application. Okay, so and we also know that KT termination is always denoted by 2, because two monomer are react, not two monomer, sorry, two oligomer or whatever chain length is there. These two oligomer are reacting and making some polymer. Okay, so what happening, two monomers are getting deactivated, so we are using this two. Okay, so use of this factor 2, IUPAC also recommended this thing. Okay, generally accepted convection for reaction destroying radical in pairs. Okay, two or in pairs, that's why it is denoted by 2. Okay, Let me see somebody in waiting room. Meghanathan, please keep your mic muted while meeting. Okay. Okay, we are here. So that's why we are using 2 at the front of rate of termination. Okay. So we are using here, just a minute. Okay. So I think it is clear why we write this sequence at the place of this. Okay. So I think you are able to understand. Okay, then rate expression we can I have already explained that rate of polymorphism is generally depend on rate of propagation. Okay, and it is equal to rate constant and the initiator concentration and the monomer concentration, you can say. Okay, so here we can replace this m value. Okay, we can replace this m value. Okay, how we find out this m value? Because we discussed that rate of initiation is equal to rate of termination at the steady state. Okay, at the steady state you can say equilibrium. Okay, at the equilibrium, rate of initiation is equal to rate of termination, and it will be equal to 2 kT m square. Okay, because two pair of monomers are getting react to termination. Okay, so finally, from here we can find out the value of m radical. Okay, concentration of radical we can find out by this expression, and we are putting this expression. So we finally find out rate of polymerization equation. Okay, so this equation will be used for solve. It is also used in some numerical problems. Okay, so radical initiator, there are two principal way in which free radical can be formed. Okay, first is homolytic cleavage. So homolytic cleavage, this bond will be will be broken and it will make radical like that. Okay, so the two electron which are making this bond are distributed equally. Okay, and it is making 2A. Okay, so it is equally distributed. That's why we call as a homolike scission. Okay, it is called as homolytic scission. Okay, transfer of single electron to or form an ion or molecule. Okay, another is transfer of single electron to or from an ion or molecule. Example, a redox reaction, single electron transfer process, some which produce only a free radical species. Okay, so it is also in some cases free radical can be changed by electron transfer. Okay, so suppose one electron is transferring from A to B, and B is now B is electron is transferring. Okay, A is giving electron to B, and now B is become a radical. Okay, so like this type of process is also happen. Okay, so because A is giving electron, so it will be known as oxidizer, and B will be reduced. Okay, due to getting electron, so it is losing electrons, so oxidation will be there, and here reduction will be there. Okay, so by this way you can understand redox reaction. Okay, to be useful source of radical in initiator system should be readily available. Okay, whatever radicals you are choosing, you need to find out very carefully, because this radical play a very important role in polymerization. We have already discussed, and we also discuss in future weeks also that how radicals are very important for the polymerization. So it should be readily available. Okay, and it should be stable. Okay, because once radical are generated, the polymerization will speed will be rate will the polymerization rate will be increased very drastically. That's why we need not to choose any radical which are not stable on the ambient or ambient condition. Okay, so it should be stable at the ambient condition, or we can at least refrigerate it. Okay, so we can keep it in a lower temperature, so it will be not reactant like that. Okay, then a practical rate of radical generation at temperature which are not very high. It is also very it is also considered condition that radical generation should not very high, because generally polymerization is occur in some solvent. Okay, some solvents we need to select, and generally solvent has a boiling point around 100, you can say. Okay, so many oil solvent which are used in polymerations have boiling point around 100. Okay, so that's why we need to select the radical which generate radical. We should any compound which form radical at moderate temperature. Okay, it is not, it should not very high temperature. Otherwise, the reaction, other reaction condition will be not follow, or we need to change other reaction condition, and it is not very easy. Okay, so that's why we should very choosy about the selection of radical. Okay, so radical initiator we have discussed about how radical is formed and how it is used for polymerization. But how radical form? Okay, it requires some energy, because you are going to make some bonds. Sorry, not you are going to breaking some bond. Okay, you are going to break some bond. So obviously you need some energy. From where you will get energy? Okay, there should be some source from where you will get energy, and particular bond will be break. It is also depend on the break bond, how much it is strong. Okay, then you need to apply energy according to particular bond. Okay, so there are various energy source which are available in literature. So thermal, okay, we very well known thermal dissociation. So by thermal dissociation means simply temperature. Okay, so by heating your solution mixture, you will be able to dissociate molecule and form radical. So thermal energy we very well know, because it is used very commonly. Then redox. So some electron. So to stabilize some molecule, electrons are sharing between molecules, and due to this sharing of electron, some radicals are generating. Okay, so it is called as a redox radical generation. Then photochemical. So photochemical means light, nothing but light. So light also has energy. Okay, because light, how light is made? Light is made by photon. Okay, and photon has also energy, HU. So by this energy, it is also possible that it can break some bonds. Okay, this light energy can break some bond, and due to breaking this bond, photochemical by for photochemical effect, we can also generate radicals for the polymerization. Then high radiation energy. Okay, high energy radiation. So alpha, beta, gamma. This nuclear energy, nuclear radiation. These radiations has very high energy, and it can also also dissociate some bonds. Okay, and some other new methods is also there. Okay, like ultrasonication and like that. These are also there, which can use to break some bonds. Okay, so first of all, we will discuss about the thermal initiator. Okay, so as it is given here, when initiator is heated 50 degree, around little higher than 50 degree, it will make radical. Okay, you can say it is homolytic dissociation. So it will give two radical. Most widely used. Okay, The thermal initiation is most widely used, not only academic but also commercial polymerization also. Okay, and it is studied also because thermally uh, by using temperature, it is very common and very old method. Okay, to use temperature to make reaction or any type of excitation in the chemical entities, we generally use temperature. Okay, that's why it is very well established, very well commercialized, and very well theoretical study. So contain moderately weak bond which undergo thermolysis at, okay. So see the moderately weak bond. Okay, so these bonds are not very hard, or you can say very strong. These are not very strong bonds. So if you thermally heated around 50 degrees centigrade, this bond will be break, and you will able to find out radical. Okay. So why will you apply other techniques? Okay, which are very costly, unit infrastructure and all this thing. That's why. So they are generally these are the examples are given here of what example? These are the example of initiator. Okay. So peroxide, I think you know the structure of peroxide. It is generally like that. Two oxygens are there. This side is called peroxide. Okay. And when it is thermally heated, it will be break like that. Okay. So oxygen making one bond, and any bond any bond takes two electron to form. Okay. So when this bond will break, it will contain radical like that. Okay, these both of these are same. I just write to make it understand. Otherwise, these are same. Okay, so like that, azo compound, peroxide and azo compound are very common initiator which are used in polymerization. Some other type of initiators are also used, like hyperoxide, okay, peristers, then disulfides, tetraazides. These are also used, but these are very specific for particular polymerization. But peroxide and azo compounds are very common, and it is used for laboratory uses as well as industrial uses. Okay, so see here one example of acyl or benzyl peroxide. Okay, is given here. Then similarly, alkyl peroxide is also given here. So peroxide and azo compound result from the available in stable form of many different compounds with a range of used temperature. Okay. Sorry, yes. Okay, so this peroxide, acyl or benzyl peroxide, this group can be acyl or benzyl. Okay, it will break like that, it will make whatever. Similarly, it is alkyl peroxide. Okay, so when this radical is formed, it is also depend that this oxygen is attached from which carbon. Okay, suppose here it is electron donating groups are there. Okay, so it will or some resonance is there and like that. So then this peroxide or this radical can be stabilized. Okay, so more it will be stabilized, it will can be used for polymers. Okay, so simply here also uh, this is the azo compound. Okay, this is the azo compounds. So here you can say this is the group is known as N. Okay, N2. This is the azo group. Okay, so this is the very common initiator AIBN 2 azo by uh, 2 azo bis isobutyl nitrile. So when this nitrogen will be removed, okay, you will able to find 2 initiator. Okay, so these are another example is given here. Nothing is new. Okay, so this is the thermal initiation. Okay, see, thermal initiation is let me just okay, so it is a KD dissociation rate is given here, and minus there. Why it is minus? Because this reaction is happening in this direction. so its concentration will be decreased. So minus di upon dt is equal to kdi, concentration of initiator. Okay, so we can write, if you integrate this equation, you will find I0 e minus kt, and if you will find out t half, then this is the equation, and it is also follow the first order equation. Okay, so this is the formula. If you, I think you know about the first order reaction also. Okay, so thermal initiator, these are some properties are given here. Initiators are used at different temperature depending on their rate of decomposition. Okay, so decomposition rate is very important. If you are going to find out, going to make a polymer of particular m molecular weight, then you need to, according to that, you need to find out initiator. Okay, because some initiator will be their dissociation rate will be high, okay, very high, so they will generate lower molecular weight polymer. And according to literature and according to your data available on literature and other sources, you first of all you need to find out that how much polymerization you require, and what are the other reaction conditions are there. Okay, so these are very commonly used initiators are written here. Okay, and their working temperature is also mentioned here. Okay, so these are used at this particular temperature only, and the difference in rate of decomposition of various initiators are related or different in the structure of initiator and of the radical produced. Okay, obviously their structure will be responsible for their decomposition. Okay, so it is very common thing, I think. Okay, it is not very, yeah. So from here we can understand the rate expression of thermal initiation. Okay, we already know that the rate of dissociation is equal to what? Uh, 2f kdi, means rate of dissociation means how much radical are finally effective. Okay, so we need to apply this f here, then 2f kdi, this all things we already know. Okay, then in this equation, if you replace this ri, rate of initiation, by 2f kdi, so you will able to find out this new expression. Okay, rp is equal to kp, then bracket m, then finally f kdi kt whole bracket half square, whole bracket power half. Okay, so similarly, if further if you write this equation in a differential form, then you will able to find out the various version of this equation. Okay, here also you can write the p is equal to mo upon m. It is conversion only. Okay, p will conversion. So m upon m upon mo. Okay, initial concentration minus how much molecules are reacted. Okay, so if you modify this thing, so at the place of m upon mo, you can write uh, at the place upon m upon mo, you can write ln 1 minus p. Okay, conversion. You can convert this thing in conversion. Okay, so finally infinity conversion, we can write this equation. Okay, we will solve some numerical also, so you will be able to find out. Okay, then here also it is simply it is also here you can say step by step we will discuss. Okay, so here also this equation is further modified. Okay, up to m infinity. Okay, so we will use one, yes, numerical, so you will able to understand. See here, what this problem is asking is the benzoyl peroxide initiated polymerization of a monomer follows the simplest kinetic scheme. Okay, the benzoyl peroxide initiate polymerization of monomer follows simplest kinetic scheme with all rate constant and F being independent of conversion. For a polymerization system with MO is equal to 2F, okay, it is initially concentration, and I0 is equal to 10 raised to power minus 2. Okay, it is the initial concentration. The limiting conversion, okay, P infinity, it is limiting conversion is 10%. Okay, to increase limiting conversion 20. Okay, so we are going to increase conversion 10 to 20%. Okay, so by putting in this equation, okay, we can find out that ln 1 minus p, this equation. Okay, and ln 1 minus p divided by, we can put these two value, 10% and 20%. So 10% will be zero point 0.1 and 20% will be zero point 0.2. So here you are putting this value at the place, at the space of p, you are putting this value. Okay, similar same, because it is this value will be cancelled. Okay, if you divide these two equation, this value will be cancelled, only I half will be remain. Okay, so it will be 20 and 10, because so you will able to find this equation. Okay, because this value will be cancelled. Okay, then if you find out, it will be 4 upon 4.8. Okay, so zero point 0.1 to zero point 0.2 you need to increase initiator concentration by 4.48. This will be the ratio. Okay, this amount you need to increase. Okay, okay, then the next topic is kinetic chain length. Okay, so just let me check. Okay, so here we are going to discuss about kinetic chain length. Okay, so kinetic chain length is nothing. Suppose I will give you a simple example. From that you can explain this kinetic chain length very easily. Okay, suppose there are 5 person. Okay, okay, there are 5 person, and they need to carry bags. Okay, and 100 bags are there. Okay, so what we do means, if we are suggesting that each person should carry equal amount of bag, so you need to you need to just divide. Okay, 100 by 5, so 20 bag, 20 bags will be carried by each person. Okay, 20 bags will be carried out by each person. So similarly it is also there. In the starting of reaction, suppose 5 initiators are generated, or you can say 5 radicals are generated. Okay, in the starting of reaction, 5 radicals are generated, and again there are 100 monomers. So okay, and each radical will take monomer. Okay, so how much monomer will we take? So we can take, okay, we can assume that each radical will take same amount of monomer. Okay, so again you need to divide 5 by 100, so 20 monomer will be there, like that. Okay, so this chain will be increased like that, and this chain will contain 20 monomer. Okay, so each chain will be 20 monomer. So we define this thing as a kinetic chain length, means how much each radical is able to collect monomer. Okay, so in simple language, so the kinetic chain length of radical chain polymerization is defined as the average number of monomer. Okay, what I am telling, same thing, average number of monomer molecule consumed, okay, by each radical. Okay, so each radical how much molecule it is taking. So in our example, there are, because there are only 100 monomers, so we assume that each radicals are taking same number of monomers, so each radicals are taking 20 monomers. Okay, so this is the thing. Okay, so now mathematically we can write the equation for the chain length. Okay, so see, this is given here. Suppose this is a radical, then this is connecting by V. n number, or we can say V, okay, because chain length is denoted by V. So V number of these molecules are connected. Finally, it is activated. It can make more bond. Okay, so like that. So V is equal to rate of propagation and rate of initiation. Okay, rate of initiator upon rate of propagation. Okay, so if rate of initiation is higher, then we will be low. What is this meaning? Rate of initiation is higher means more monomer will be there. Sorry, more radicals will be there. Okay, if Ri is higher, then more radical will be there, but monomer concentration, suppose we are keeping 100 fixed. So each initiator, sorry, each radical will get small number of monomer. If Ri is there, then each radical will get small number of monomers. So that's why the chain length or kinetic chain length will be less. But if Rp is higher, means rate of propagation is higher, means suppose there is only two radicals, but rate of propagation is very high. Okay, if rate of propagation is high, then also indirectly we are saying that chain length is very high, so kinetic chain length will be high. Okay, so finally we can say that kinetic chain length is depend on Rp and Ra. Okay, it is directly proportional to Rp, and it is inversely proportional to Ri. Okay, so rate of initiation is equal to rate of termination. So we can further write this equation like that. Then, uh, yes, rate of propagation, we know already. We have studied many times this equation. Rp is equal to Kp, m monomer concentration, and radical concentration and monomer concentration, and termination is equal to 2 kt m square. Sorry, radical concentration square. So if you put this value here, okay, you will this m square will be cut from this m. Okay, there only kpm on the numerator and 2 ktm square at denominator. Okay, then again by this rate of initiation equation, okay, you can find out mi. Okay, because we know na what is the mi. Ri, yeah, by this equation. By this equation, if you find out mi, not mi, sorry, what I'm telling, sorry, it is not mi, radical concentration. Okay, so radical concentration we can find out like that. Radical concentration will be equal to Ri upon 2 ki and power half. Okay, so if you put this value here again, okay, you can put this value here. So see, huh. Then at the place of Ri, you need to write this. Okay, rate of initiation we have already discussed 2f kd. So if you put this value here, finally you will get this equation. Okay, so finally this is the equation for kinetic chain length. Okay, then kinetic chain length is new term which we are discussing, but xn is polymerization, degree of polymerization. We have it is we are discussing from last 2 weeks. Okay, so degree of polymerization means how much polymerization is there, extent of polymerization. So it is obviously it is depend on xn, it depend on kinetic chain length. If chain length is higher, then degree of polymerization will be higher. Okay, but as we know that termination can be occur by two type of reaction. First is coupling, and second is disproportion. Okay, so by coupling reaction, we know that it is chain length will be just double in one step. Okay, when these two oligomer will react, they will make polymer, but their chain length will be just double. Okay, so degree of polymerization just two of kinetic chain length. But if disproportion is there, then if degree of polymerization will be equal to chain length. Okay, but in any equation, the only coupling or only disproportion is not only responsible for the complete reaction, Okay, some part of coupling reaction will be there, some part of disproportion reaction will be there. Okay, so finally we can write the expression in this form: Xn is equal to BV. So this is the kinetic chain length, and this B representing that how much you can say the average number of initiator fragment per polymer molecule. Okay, so the average number of initiator fragments per. Okay, so how much means initiators are fragmenting. Okay, so the average number of initiator fragmented poly uh, per initiator fragments per poly molecule. Okay, so see, if this chain has two initiator molecule at each end, then we can say that it is made by coupling. Okay, and if it is has only one like that, then it is made by disproportion. So by in this form also we can find out that the termination is occur by coupling or disproportion. Okay, so by using this B, which is the average number of initiator fragments per molecule. Okay, also we can find out the Xn. Okay, the another way of 2V divided by 2 into A. And what is A? A is fraction of propagation chain undergo termination by coupling. Okay, so A is representing the coupling reaction. Okay, fraction of coupling reaction. So suppose in some case we just assuming that A is equal to 1. Matlab fraction is 1 means complete reaction is occur by coupling reaction only. So if you put the reaction coupling, so Xn will be equal to 2 nu about 2 minus A. Now I am putting A value 1, so it will be 2 minus 1. So 2 nu upon 1, or you can say 2V, not nu, sorry, 2V. Okay, so what is this? Means the Xn degree of polymerization is just double of kinetic challenge. Okay, why? Because the complete chain, sorry, the complete reaction is occurring due to coupling reaction only. The complete reaction is occurring due to coupling reaction. If we are assuming, then it will be equal to 2V. So this formula you can check like that. Okay, for understanding. Okay, so now we are going to discuss about the effect of monomer and initiator concentration. Okay, effect of monomer and initiator concentration. Okay, for thermal initiation. So rate of polymerization is proportional to according to this equation which we has derived, it is proportional to m and I. So we can say rate of propagation will be depend on um, monomer concentration as well as initiator concentration. So either you will increase monomer concentration or I initiator concentration, the rate of polymerization will be increased. Okay, obviously, when you will increase concentration, what is the initiator? Initiator is also making some radical, and radical is also we are using radical as a reactant. Okay, so finally these both are reactant. So whenever you are increasing the concentration of reactant, the rate of reaction will be increased. So same thing is here. Okay, this expression is also saying same thing, that when we increase the rate of reactant concentration, the rate of reaction will be increased. Okay, so either you are increasing m or you are increasing I initiator, which will produce radical. Okay, so the reaction rate will be increased, but the chain length. So if you are increasing the concentration of monomer, the chain length will be increased. Okay, the chain length will be increased. Okay, but as you increase the initiator concentration, more radical will be formed, and if more radical will be formed, then monomers will be distributed in these radicals. Okay, so that's why the chain length will be decreased. Okay, so this expression is also saying same thing which we explained by general discussion. Okay, so here you can say when m will be increased, rate of polymorphism will be increased, and when I increase, rate of polymorphism also increase. But when m will be increased, molecular weight will be increased. Okay, obviously molecular weight will be increased as m will be increased, but as I will be increased, the molecular weight will be decreased. Okay, because where I will be increased, the monomer will be distributed in more radicals. Yes. Okay. So this is the selection of thermal initiator. Okay. So selection of thermal initiator is very important. Okay. It is depend on its property, its half lifetime. Okay. How long time it required to half lifetime. Okay. So and half lifetime is also depend on the temperature. At what temperature your reaction is going to happen. So these all things you need to keep in your mind. Then only you can select particular initiator for your action. So some examples are given here. AIBN. Okay, so at 50 degrees centigrade, 74 hours is half lifetime, 70 at 4.8. Okay, so it is like that. So according to that, you need to find out if half lifetime is very high, then also it is creating problem. Reaction will be rate will be very slow. Okay, and if half lifetime is very short, then also it is very problem. Okay, so according to your application, okay, which polymer you are going to synthesize, how much molecular weight you are required, this all things are required for that. Okay, so initiator efficiency again. So we discussed that, okay, we are taking this initiator and this condition, this temperature, we require this half lifetime, all conditions are set, and according to calculation you are going to add some required concentration of initiator. But one another aspect is how much your initiator is efficient. Means you add initiator, but 100 out of 100 initiator molecule will not take part in reaction. Okay, then what will happen? So obviously you need to increase the concentration of initiator to meet the requirement of particular concentration of radicals. Okay, so that's why we can see here this diazo initiators reaction is explained. Okay, so see here in the first reaction, it produced two radicals, but again these two radicals are combined or these radicals are regenerated and all these things. Some side reactions are occurring and like that. So this initiator, these radicals, you can say are not available for the reaction. Then we are not getting the required condition. Okay, which we need for reaction. So initiator efficiency is also very key aspect. Okay, to find out the rate of propagation and okay, rate of propagation mainly, then kinetic chain length and all. Okay, so see, this is the peroxide, you can say benzoic peroxide. Okay, when it will be dissociate, it will make two radical. So we require two radical for reaction. Okay, this is our object. We require these two radicals. But some side reaction are occurring. Okay, see what happened. These two radical can form another molecule with CO2. Okay, so you lost these two radicals. Okay, it is lost. Then this radical also can release CO2 and make this benzene radical. Okay, so we do not require this radical again. So we are losing this monomer, sorry, radical. Similarly, this benzene radical can react and make another thing. Okay, so these are the side reaction which are affecting the concentration of initiator. Okay, so we need to find out that how your initiator can be react by side reaction. Okay, what are the particular conditions to inhibit this side reaction? Okay, so the required efficiency of your initiator can be occur. Okay, So this thing can be also should be considered. Uh, okay, these informations are available in literature, or sometime we get new things by the uh, experiment. Okay, while the experiment we just find out some new things, and according to that we need to analyze. Okay, why by adding the particular concentration of initiator we are not able to find out the required molecule or required polymer. So there is something is missing. Okay, so you need to find out like that. Just a minute, I will start within 2 minutes. Okay, now we will discuss about the redox initiator. Okay, so many oxidation reduction reaction produce radical that can be used for initiate polymerization. We will discuss some example in next slide. Okay, initiation is moderate temperature. Again, it is 0 to 50 or even lower. Okay, so some redox system involve direct electron transfer between reactant and oxidant, while other involve the intermediate formation of reactant and oxidant complex. Okay, so we will discuss some example here in this slide. Okay, so peroxide, see this peroxide is already used for radical formation for by thermal initiation also. Okay, and this peroxide also can be used hydrogen peroxide here. It is hydrogen peroxide. So hydrogen peroxide can be used for uh, formation of radical by this reaction. Okay, so see one. This is the OH minus. Okay, so H2O2. We can write like that. Just a minute. Okay, so it is like that. Okay, when it is making bond like that. Okay, so you can say Fe plus 2 to Fe plus 3. Okay, another reaction what is happening? Fe plus 2 to Fe plus 3. So it is releasing one electron. So this electron will be used here. Okay, so this electron is transferring from this molecule to this molecule. Okay, so it is making one negative ion, one radical, and Fe plus 3. Okay, so this is calling electron transfer. Okay, so here uh, it will be Fe plus 2 will be oxidized. Okay, it will be oxidized. Fe plus 2 to Fe plus 3. And it is known as a reductant because it is working as a reducing agent. Okay, so Fe plus 2 is reducing agent, and this electron sharing is happening. Okay, similarly Fe plus 2 to Fe plus 3, see all things are same, electrons are losing, and it is giving in the same according to first example, and it is making different various type of radical. Okay, so this type of reaction also can be redox initiation. It is called as a redox initiation. Okay, so SL peroxide can be used in organic media along with amine as the reductant. Okay, SL peroxide. Then benzyl peroxide and N,N-dialkylamine also can be used. Okay, so see now it is a uh, the combination of variety inorganic reductant and inorganic oxidant. Okay, so here also same thing is happening. It is uh, dissociating like that. SO4 minus 2, it is common species, we already know, and it is SO4 minus, then one electron radical. Okay, so it is also producing like that. So there are many reactions where you will able to find out different type of radicals which can be used for polymerization. Okay, then finally rate expression for redox initiation. So here also rate of polymerization is equal to Kp m Ra upon 2 Kt. Okay, but here Ri जो rate of initiation है is equal to Kd, then rate of sorry concentration of reduction and concentration of oxidation. Okay, so if you put the Ra value here, you will able to find out this expression. Okay, Mi is equal to Kd upon 2 Kt, then Ri, so it will be just a minute, Kd half, yeah, 2 Kt, so Kd is given there, the reduction, oxidation, yes, right, yeah, yes, so you will able to find out this equation. Okay, now we will discuss about the photo initiation. Okay, as we already discussed, where light will be fall. Okay, light has also some energy in the form of h nu is equal to h nu. Okay, so when by using light also we can produce some type of radicals. Okay, so here when light is fallen this molecule, it will dissociate from here. Okay, and it is making two radical. Okay, similarly there are another examples are given here which are also making radicals by using of light. Okay, so rate of accretion for photoinitiation. So it will be now it is not depend on the concentration. Okay, it is depending on uh, IA. Okay, so uh, 5 days is the number of radicals produced per light photon absorbed. Okay, how much radical produced and per light photon means in one photon how much radical are produced, it is known as 5 days. Okay, and F is initiator efficiency is defined below. Okay, you can say that n radical are formed, okay, by the falling of light, but you can say n minus x radicals are only available for reaction, so efficiency is less. Okay, so you need to find out like that. Okay, then you can find out Rp is equal to Kp, and if you put the value you will able to find out this one. Okay, but rate of initiation is already only depend on IA. Okay, intensity of light. Now initiation by ionization radical, sorry, initiation by ionization radical radiations. Okay, ionization radiations means some radiations are falling like nuclear radiations and which has very high energy, and due to energy of these radiations we are also able to produce some radical. So generally radioactive source and particle accelerator are used to initiate polymerization. high energy radical like gamma and X-ray. Okay, so X-ray and gamma, this radiation has very high energy, and when this radiation energy falls on these molecules or this whatever this compound is, it will make some radicals. Okay, and this radical can be further used for the polymers. Okay, sometimes we can also use particulate radiation. Particulate means we are using some particle like electron, neutron, and alpha particle. So this particle which has high energy also can hit the molecule and can generate some type of molecule. Okay. So student, here only I am stopping because it is already 2 hours. Okay. Anyone, any question you can ask. I will give you 2 minutes. Okay. I am giving you 2 more minutes. If you have any question, you can ask. Otherwise, you can leave the meeting. Okay. If you have any question, you can ask students. No question. If you have a question from third week, if you have any question in assignment, ongoing assignment, if you are not able to understand, then also you can ask. Okay. So now I am going to stop here. Okay, we will meet in next week.